This is part 3 of section 6.4. Now we're going to talk about how we can work with vectors algebraically, now that we understand geometrically what might be going on. So in order to work with these geometrically, we're going to consider vectors located in a Cartesian coordinate plane. That's our normal graphing grid. And recognizing that the initial point of a vector is not really relevant, so we typically draw vectors with their initial points located at the origin because 0, 0 is the easiest thing to deal with. If we have a vector located in the Cartesian coordinate system and we've placed the initial point at the origin, we call that particular vector a position vector, okay? Notice that with a vector positioned in this way, the terminal point of the vector completely defines the vector. So if we have we have a position vector, we know its initial point is the origin. So all we need to know is its terminal point to draw the entire vector, okay? So for the position vector v with initial point at the origin, 0, O, and terminal point p, v1, v2, we denote this vector by v, vector v in bold, is equal to OP vector, is equal to, these are little pointed brackets, okay? These are not parentheses. v1, v2. This is a vector, this is a point, okay? We call v1 and v2 the components of vector v. v1 is the first component and v2 is the second component. You know, these are different algebraic systems than what we've been dealing with, and I've tried to make a distinction between everything we do with vectors being different from scalars. And even though things are not the same, you'll find that they kind of rhyme. Okay, so these are parts of the vector, but they also kind of coordinate with your x and y coordinates. Okay, but it is important, again, a point in parentheses, an ordered pair. Points have no magnitude and no direction. It's just a point. Position vectors have both, so they are different animals. Okay, the magnitude of the position vector, v1, v2, follows directly from the Pythagorean theorem and the distance formula, because the distance formula comes from the Pythagorean theorem. Remember, the distance formula is the square root of x2 minus x1 squared plus y2 minus y1 squared. One of these points, one of our initial points, is the origin, so the subtraction is just going to be x2 squared, y2 squared, which kind of coordinates with this, okay? So if you have a position vector, then you can calculate the magnitude of the vector by taking the square root of the sum of your two, the squares of the two components, okay? Notice that I mentioned this earlier, magnitude and absolute value are very closely related concepts. They both can be defined as a distance from 0, okay? An absolute value is defined as a distance from 0 on a one-dimensional number line, okay? Magnitude does something similar. If we're talking about a position vector, it does say how far the end point is from 0, but it is in 2 dimensions, okay? And then once you get into Calc 3, you're going to be talking about these things in 3 dimensions. Okay, so it's like absolute value on steroids. It's a different definition and it allows us to push things further into further definitions, okay? If 2 equivalent vectors are located with their initial points at the origin, then their terminal points should be the same, okay? So this allows us to say that if we have 2 vectors with their components for vector v as v1, v2, and vector w as w1, w2, then the 2 things are equivalent if and only if your first components are equal and your second components are equal. Okay? So what do we do if we have a vector, but it is not located in with its initial point at the origin? Well, it's really easy to figure out how to do that. You just look at congruent triangles. And basically, all you really need to know is the length of this, and you can calculate this. And so all you have to do, if you have something located that is not located at the origin, to get it there, you subtract terminal minus initial. Terminal minus initial. Here it is written in this form. So if you have a vector with initial point P, which is x1, y1, and terminal point Q, which is x2, y2, then the position vector is x2 minus x1, y2 minus y1. And it is important. This is not a line, which we dealt with earlier in the course, where it didn't matter which order you did it in. Because these have a direction, it is important that you do the terminal minus the initial. Otherwise, you're going to have things pointing in the wrong direction. Okay? We write the 0 vector with the two components 0, 0. And to write the opposite of a vector v, which is v1, v2, each of your two components becomes the opposite of what they were. All right, so let's do some calculations. The vector v has initial point P and terminal point Q. We want to write v as a position vector. So our v vector will equal terminal minus initial, so 1 minus 6, comma, 1 minus a negative 4. So this becomes the vector negative 5, 5. Okay. Now do the same thing here. If our initial point is negative 1, 4, and our terminal point is 2, negative 3, then the vector we are looking for will be 2 minus a negative 1, so 2 plus 1, and then negative 3 minus 4. And we end up with the vector 3, negative 7. Now, we could go through the proofs for all of this, but here are your basic arithmetic operations and properties of vectors. U is a vector with components u1, u2. V is a vector with components v1, v2. And W is a vector with w1, w2. C and D represent scalars. Okay, so then we have all of these properties. Okay, so if we have, position vectors here, and we want to add the vectors v and u, we get to add their first components and add their second components, and we've got it. V minus u, you subtract their components in the order here, and you've got your answer. Okay? So vector addition, vector subtraction gives vector answers. A scalar times a vector, you get to multiply each component by that scalar. Okay? And we've already talked about how vector addition is commutative. Now here, we are adding vectors, and that is a mistake right here. That should not be in italics. Sorry about that. So if I have u plus v in parentheses plus w, that is the same as adding v and w first and then u. This is called the associative property. And we already know that we have that property when we're adding real numbers, so scalars in this vocabulary. But it was not particularly obvious from the beginning that it would work with all vectors. Okay, now let's look at these two. And they're very similar in that they're both distributive properties, but they do say very different things because we have here, this is scalar addition, and this is vector addition. And those are two different operations, so it's not particularly obvious. But what this one says is that scalar multiplication, which is what we have right here, distributes over scalar addition. So it's scalar c times vector v plus scalar d times vector v. Okay? Here, this is scalar multiplication times vector addition, and it also distributes. But these are very different properties, but they do work the way we would like them to. And here we have a scalar times a vector, and this says this is another associative property that says we can multiply the scalars first and then multiply the vector if we so wish. Okay? One thing I do want to point out is that we do not use the dot notation for scalar multiplication. And the reason we do not do that is that that symbol means something totally different when it comes to vectors, and that's what we're going to cover in the next section.